Hey guys, are you ready for it? Because we're gonna do Lorentz transformations and the space-time interval, otherwise known as special relativity. Shall we? I'm down. I'm actually so down for this right now. So yeah, maybe title this special relativity. We'll see that the word special refers to that this is so-called flat space-time, space and time um, will have a specific relationship. This is the geometry of space-time. It is the case that space and time can move, bend, warp, stretch. Really, it's like stretching, bending, and moving. That's general relativity. Special is just how space and time relate, centered on centered on a few core principles. One is space and time clearly, as we observe it, is smooth and continuous. It's homogeneous, meaning it's the same everywhere. And uh, the most fundamental principle, it's like a postulate, but it's also an observation. It coincides with experiment, and it seems to be necessary to have anything exist at all. Once you sort of go through the logical steps, you realize that the speed of causality, which we'll call c, the maximum speed of causality, that we appear to be in a universe where certain events can cause certain other events and certain events cannot affect certain other events. So maybe have like event A affecting event B, but event B does not affect event A. In other words, it doesn't go backwards. And maybe event C here, right, is too far away for event A to affect it. Maybe they happen at the same time, really far apart, and maybe they both affect event B, maybe not, right? So the maximum speed of causality we'll call c. Light, which we know, definitely need to know, is an electromagnetic wave. Uh, comes in little packets called photons, which are massless. Since it is massless, it reveals this maximum speed. That argument or that realization is for another day. I'm just going to say that it does, that the models of reality that, Einstein proposed and particle physicists have revealed, um, mainly Einstein, right? Although he had many contemporaries working on this also. These are models of reality. We have a concept called mass, which is inertia. If something doesn't have mass, it just has no inertia uh, inherently. Its inertia comes from its energy, which we'll talk about later. So I have to be a little careful in how I say this. But it has no inherent mass, which means it reveals this maximum speed. So the point is, we say then c is the speed of light. But it's actually the maximum speed of causality revealed. It's also the speed of gravitational waves. Gravity is massless. Gravity itself, meaning the effect of gravity, is massless. It's caused by mass, but it's not, it itself doesn't have a mass. Gravity itself doesn't have mass. So the speed of gravity also travels at the speed of light. The speed of what are called gluons of the strong force also don't have mass. That speed inside of a proton itself or in between protons, although the protons themselves are a residual strong force, so maybe that's a little different. Those are mediated by what's called pions. But the speed of gluons inside of a proton is the speed of causality as well, right? So the point is space and time. So this reveals the connection between space and time. I would love to dwell here longer. And for those of you who are in class and you might be listening right now, you can tell I would love to sit here longer and go into this. I'm giving the short version, claiming it to be true or at least accurate as a model, right? I'm claiming this to be accurate as a model of reality. There's experimental evidence for this galore. Um, The famous Michelson-Morley experiment shows that the speed of light is the same in all reference frames. Because this reveals the connection between space and time and is the maximum speed of causality, we must have this be the same in all reference frames. And I don't want to dwell here too much because I want to go on to Lorentz transformations, but I find this to be pretty significant, is that the whole point here is that c, right, the speed of causality, which, yes, we will refer to as the speed of light from now on, because that's what we're trained, because light is the most prevalent massless object in the universe that's just abundant in everywhere. The other ones aren't really as prevalent, must be agreed upon by all observers. And I'm making a claim that I promise you has enormous amount of experimental and logical basis. I'm just claiming it just to plant the seed, is that if this was not the case, that literally atoms couldn't exist. The whole field of chemistry would break down. You could not have a biological mechanism. We would disagree on the nature of form. Like otherwise, form could not exist. There would be no physical form. I think we can all agree that there's at least an appearance of physical form that has properties that are predictable, that behave in a certain way, no matter what you're doing, no matter who you are, the way in which physical matter works is the same. Otherwise, physical matter would be incoherent. Physical form, I like the word form, would be inconsistent and I love the word incoherent. So that means for two observers, and here's what we mean by an observer. Say there's somebody who has an eyeball and they're watching, that's a creepy eyeball, and they're in reference frame S. And then somebody else, that's part of a face. I'm not going to draw the face because it's probably going to be creepier. There's maybe somebody, it's usually a rocket ship, although that's kind of weird. There's a rocket ship traveling at some speed. That's reference frame S prime. And that person has an eyeball or a camera also, or is receiving information in some different way. So really, light encodes information, like a black body. It encodes the temperature or electron transitions. It encodes that information, right? And sometimes it can be tricky. You can be like, well, what information is it encoding? But it's definitely got a frequency and a wavelength. And that information is moving through space. Frequency is frequency, stays constant the whole time. So it's like whatever emitted it, like that is now encoded in that photon. So you can think of it as like the speed of information cannot be instantaneous. And if you think of counterexamples of this, I'm happy to talk about it. This has been shown over and over and over and over and over again from many different angles that I do not have time to go over in class that I want to. Like I said, I want to dwell here, but we need to get to the fact that in both of these reference frames, we're going to call this x t as its coordinate system. Maybe it's at position 2, and then time is like 1 second, 2 second, 3 seconds. We're going to have x be in light seconds and t be in seconds from now on. Maybe years and light years we might switch to, but then what we realize is that the speed of light is 1 light second per second. So the speed of light is 1 in these units. We're not using meters. This is not meters. This is 300 million meters because that's how long a light second is. A light second is how far light travels in a second, but I'm not using meters. It's like I converted to inches or I converted to centimeters. I'm converting to light seconds as my ruler. I have a light second ruler. It's a big ruler, right? It's about 8 times the circumference of the Earth, right? So we actually set c equal to 1. These are called natural units. A meter is not a natural unit, right? A meter is a very human unit. So natural to the universe, let's just set it equal to 1. It makes our math so much easier. I'm still going to use c in the equations, but it just makes the math so much easier. Then s prime will have coordinates x prime and t prime, which means that this is agreed upon by all observers that light, or just anything that's massless, must be this, and at the same time, I'm trying to box that. Hold on. I drew a little close. And at the same time, I'm getting there. X prime is plus or minus c t prime. This is the big important thing, that these are both true at the same time. Got there. It's pretty easy. I probably could have just started there, right? Let's move on. So that's the big important thing. In fact, that's really where we want to start. That both of these are true at the same time, which means we need a model of space-time such that both observers agree to this. Now, what I'm going to do also, though, is I realize I actually don't want to do x and t, and I apologize for that. I want to do delta x and delta t. But really, I want to switch to a calculus nomenclature. We're not going to do calculus, but I'm going to use the same symbols, nomenclature meaning language, symbols, right? Notation, maybe is a better word. Thank you. And I'm going to use dx. D as in change in. This is still change in x. So it's funny because those of you who are not familiar with calculus, just consider this delta x. It's just going to be nice later on when we, maybe can include calculus, which I'm not going to require, but it's just nice to align with it. Those of you who are in calculus are going to notice that I'm going to be cheating. That this usually you set dx, you take the limit as it goes to 0. We're not doing that necessarily. We can later, but dx is still just delta x, and I'm not taking the limit as it goes to 0. So dx could be 5 light seconds. dx could be 20 light seconds. It can be anything. It still is a delta x. And obviously, change in t will be dt. And obviously, t primes and x primes. So that means we need dx equal to be plus or minus c dt, and dx prime equal to plus or minus c d prime, right? So position equals velocity times time, or change in position equals velocity times change in time. And remember, this is for light only. So for light rays, but both need to agree at the same time. So how can we have both agree at the same time? So we need to have something that everybody agrees on in terms of how space and time are related. So how can we get all these together? So here we're going to do two things. We're going to do what's called the space-time interval, and we're going to do what's called Lorentz transformations. These are equivalent. So we have three equivalent things here. We have 1, 2, and we're going to have 3 over here that are all equivalent. 1, 2, 3 are all equivalent. So this, where both of these are true at the same time, gives us the space-time interval. Pretty cool. I love this. I actually really love this. It's pretty amazing, right? I'm going to derive it real quick. So that means we have this and this are both true. To get rid of the plus minus, we square. So that means dx squared equals c squared dt squared, and remember we need and, that's an and, sort of, dx prime squared equals c squared dt prime squared. And that therefore this is obviously if we took the square root, the plus minus solution would come in because it could go in the negative direction. So we need to take that into account. It's actually important because we're going to have what's called a light cone. That light is going either forward or backward, and we need it to go forward and backward at the speed of light so that we can't be going really fast and like shoot light out of the tail of our, cannon, and then the light just sits there. We need light to travel the speed of light forward and backward in the x direction. And obviously, we're ignoring y and z direction. I hope that was apparent from the start. We're just going to isolate a one-dimensional situation here. 3D, totally possible, but a little out of the scope. Let's just start with one dimension. So that means let's subtract dx squared over. Please do not get lost with this algebra. It's extraordinarily simple algebra. Which means these both equal zero at the same time. The only way for them both to be zero at the same time is that they equal each other by some like multiplier we'll call k, just some like dummy multiplier. It can be shown pretty straightforward, and I'm going to sort of skip it. I'm just going to say it just because I want to move on, that k must equal 1 in order, and that's to do with the homogeneity of spacetime, which means that certain reference frames won't have double lengths and double times. Its space won't just get bigger in all of the same ways. You might have some aspects changing individually, but k equals 1 due to the homogeneity of space-time. I'll let you guys think about that and what that means, right? But the point is that means this equals this, and we actually establish, I'll get to 3 in a second. I just realized I need a little more space. Little more space, time, get it? Space is time. Time is space, right? Time is just a fourth space dimension that behaves differently. This is how they relate. So that means we define this quantity. So if this equals this, that means they both equal the same thing. So we define ds squared. This is called the space-time interval. Since these equal each other, because they need to both equal zero at the same time, it means they equal each other all of the time. Now, if you sit there long enough and think about it, you're going to realize that's true. At first, you might say, well, what other mathematical functions could work? It can only be this. I'll invite you to try other ones. The key has to do with this and what this means. And I'm happy to talk about that in more detail, but I'm just going to leave it be for now. Claim it to be true. Realize, Einstein went all through this. We don't want to just rely on Einstein. We want to do it ourselves. This is us trying to do it ourselves, right? Actually, a man named Hermann Minkowski figured this out, who was a friend of Albert's back in the day. And ds squared equals this. And this. That's a prime. That's a prime. This is the space-time interval. This is agreed upon in all reference frames. Or we say like all inertial frames, meaning all frames of constant velocity, right? We're not going to go through non-inertial frames here. So cool. I hope that makes sense. I hope this logic makes sense. This is really important. We're going to be calculating this in different reference frames and realizing what it means. Now, one interesting thing that it means, side note, right? First of all, here's the math. It makes sense. We define this. This is defined now. I want you guys to know these formulas and what this means, right? Where it comes from, right? But most importantly, we're just going to practice using it. But hold the phone, right? If ds squared equals, c squared dt squared minus dx squared equals also c squared dt prime squared minus dx prime squared in the other reference frame, Doesn't matter. We all agree on the speed of light, so therefore we all agree that this is zero for light, which means, dx equals c dt and dx prime equals c dt prime. We're going to get zero. But it turns out because they both need to be zero at the same time, they both equal each other non-zeroly, right? So a few interesting things happen. First of all, if, you know, uh, if you go farther in space, you'll notice then and this is true for the primes as well, then ds is less than zero, and that's impossible. That is called space-like. It means you're moving only through space and not through time, which is like teleportation, which would be like, uh, impossible influence, right? Influence is out of reach. Causality, influence causality is out of reach. If dx equals cdt, then ds equals zero, and we already said that that is the speed of light. That is called light-like. This is also called the null trajectory, and this is what light does. This is like on the boundary of influence. This is like on causality boundary. When we graph this, it should make sense, but I hope this makes sense on its own. If you move less in space than you do in time, that's normal. That's what you're doing right now. Feel that there's a motion through time that you're noticing. Well, it's less of a motion and more of a propagation, which is true because you are made of waves, but it's also true in the sense that I wouldn't consider this a motion through time. It's just more like we're noticing changes that we then mark as time, right? And causality has a limit, right, to what that can be. That means ds is greater than zero. You can take, sorry, ds squared. Sorry. If this is less than this, then ds squared, which you cannot take the square root of a negative number. That's impossible. So that means it's out of reach. Here it is equal to zero. You're on the causality boundary. That's the null trajectory. That's light-like. This is called time-like. Are you moving through time right now? Yeah, so you're time-like. That's how you remember that. It's okay to move just through time and not through space, right? Or to evolve, to propagate, to experience time and just be in the same point in space. This is, causality possible. So this is impossible, this is possible. So space-like, light-like, and time-like. Please know those words and these conditions for them. It's pretty easy, has everything to do with this space-time interval. We're going to graph this in a moment, which is going to be helpful as well. The next thing you want to do is say, okay, for S prime, the moving frame, moving at speed v. And v is dx dt or delta x delta t, right? Change in position over change in time, right? So that's our speed. That's really important, which means that dx equals v dt. It equaled c dt for light, but for the object itself, it's moving at dx dt. But in its own frame, right, this is xt in the S frame, right, the outside frame. In its own frame, right, an object is never moving relative to itself. Notice that you are never moving relative to yourself. So dx prime is always zero in something's own frame. An object never moves relative, that's why it's called relativity, to itself. This is profound. You're not moving down the street is moving under you, and I'm serious. You might laugh and joke, oh, that's just an illusion. No, that's actually reality. Like if you're riding in a car, the forest and the road is actually going backward relative to you. So if you enter a state where you get out of your programmed mind of saying, oh, I'm moving, and you realize, oh, wait, no, the ground is actually what's moving, you'll notice it'll switch. And you realize that it's actually, oh my God, I'm actually always still relative to myself. It's very present. It's great meditation, right? Very present in body, right? Realization. And this model is entirely based off of it. So if dx is zero, what does it say about the space-time interval? It says then ds squared equals c squared d cd prime squared, because dx is zero. Because remember, this was minus dx prime squared, so that just goes away. That's zero, right? Which means that ds squared corresponds to a time. That in your own frame, in the moving frame, ds, the space-time interval, becomes what we call a proper time. It becomes an invariant time because this is invariant. The space-time interval is agreed upon by all observers. So that means like in the moving frame, right? You have something moving, right? Inside of it, right? It's moving at a speed v from the outside. So I have my observer here, S, and this is S prime, right? This is an eyeball, right? And I have some grid here. But inside itself, inside the moving frame, it doesn't experience any motion. So that means ds squared, sorry, S is capital S is usually used for reference frame. Little s is usually used for space-time interval. Please do not get those two confused. Apologies if I just realized right now we're using the same letter, right? So these are reference frames. This is the space-time interval, right? ds squared equals c squared cd prime squared. What we do is we replace dt prime with something called d tau. D prime is any general, right, coordinate, but tau is special. Tau is when you're inside the moving frame. We call d tau proper time. It's defined as ds over c, or d tau squared equals ds squared over c squared, because look, it's right here. It's right here. It's when inside the moving frame, that experience of time is called proper time. So this is the time experienced inside the moving frame. Please rewind this until it makes sense. Time inside the moving reference frame. So if I'm in a car, it's the time I experience. And my position relative to myself is always zero. But notice how it's connected to this invariant quantity, which means that all observers agree on it. All observers agree that I experience that amount of time. So proper time is agreed upon by all observers, and that's pretty cool. Now let's derive a formula for it. So again, v is dx dt in the non-moving frame. Remember, those are no primes, right? So you know it's moving when you have the primes or you have the tau. This is the moving frame. If you don't, this is the stationary frame, or I like just saying it might not be stationary, the outside reference frame, because we're going to have yeah, you'll see. Cool. So let's write the space-time interval, but instead let's write it as c squared d tau squared, right? Equals c squared d t squared minus dx squared. But dx is v dt. So c squared d tau squared equals c squared dt squared minus v squared dt squared. How did I do that? Dx is v dt. Just from this. Distance is velocity times time. It's just kinematics 101. Don't overthink it. We're just using different notation. Same exact physics, though. And we derive this space-time interval. Remember that d tau is ds squared or d tau squared is ds squared over c squared, right? So I just substituted in for the spacetime interval. And now what I'm doing is solving for d tau in terms of dt. So notice I fact out dt, I divide by c squared, and I get, I'll let you do that algebra, dt is the square root of 1 minus v squared over c squared. Sorry, d tau is the square root of 1 minus v squared over c squared dt. What we do is we define a letter gamma, not for light, even though this has to do with the speed of light, equal to, this is called the relativity factor, equal to this, and therefore we say d tau is dt divided by gamma. So I want you guys to know gamma. This is going to be really important. This square root is going to show up everywhere. It's not coincidence. It's just showing up everywhere. It comes from the geometry of space and time. This is the geometric relationship between space and time. You can see, I don't know if you notice, it's a hyperbola. This is a hyperbolic function. We're going to be graphing hyperbolas later. But this is called time dilation. If you look at this for more than 2 seconds, you realize that this is always less than 1. Therefore, d tau is always less than dt. That a moving frame always experiences less time than the outside frame. It's huge. That if you're moving, time goes slower because of this subtraction here. That your inside time, because your dx is 0, your dx prime is 0, but outside it's not. So because we all have to agree on the speed of light, this subtraction makes d tau less than dt. Isn't that kind of cool? That's kind of cool. So one last thing. So you can pause and rewind that. There's not much more to say with that, except we're going to do some problems, do some examples. I'm just giving you guys the equations. The last piece of the puzzle, and this was number 3, Lorentz transformations. I'm just going to give you the equations. I'm not going to derive them. It takes a minute to derive them. What do we have so far? We have the space-time interval. We saw that this produces time dilation. We saw, and this is for, dx prime equal to 0, right? Inside the moving frame, right? Well, we saw that this comes from the fact that, dx is plus or minus c dt, and at the exact same time, we must have the moving observer also measure the speed of light to be the speed of light. Great. Turns out this is also equivalent to simply transforming. You can literally just solve for the coordinates in the new system. You don't have to do a special case of dx prime is 0. So if you have any coordinates, like I'm at position 4 at time 10, or I'm at position 8 at time -2, great. Any coordinates can be transformed to the new coordinates. And we're going to graph this in an example later, but I'm just going to give you the equations. This is called the Lorentz transformations. So the Lorentz transformations have this exact formula. You guys ready for it? So all you got to do is this. X prime is gamma. Remember, gamma is 1 over the square root of 1 minus v squared over c squared. And typically we have c as 1. And if c is 1, then v is in terms of v is in terms of speed of light. So there's our gamma term, just the relativity factor, times x minus vt, where v, of course, is dx dt. So these are absolute coordinates, not change in x, not change in t. These are absolute positions in space and time. These are change in space or time. Careful. And then we'll do it this way. Ct prime equals gamma times ct minus v over cx. This is not intuitive or obvious, but it's pretty simple formulas. Don't overthink it. You're just going to look at this. You're going to plug in values. Typically, c is going to equal 1. And if c equals 1, we're going to rewrite this as this. And then you'll notice it looks like the first one. You notice those two look the same, right? So I'm just going to do these, but I'm going to give this one because this one's going to become important with the C's in it. If we actually want to prove that this is equal to this and equal to this, maybe on your own, if you want to, tinker around with the algebra for, take you half an hour, you can show that this is the same as this is the same as this. These are just three different ways of saying the same thing. One, two, three. These are the Lorentz transformations. Cool. I'm going to pause. I'm going to stop for a second, right? Please rewind the video if that made like half sense. I want it to make lots of sense. It's going to make more sense when we do examples. What I wanted to make sense there was the math, like just the math, and in my words, and I hope I wrote it down, what the symbols mean. So please know what the symbols mean. Please know the equations, and we will practice later. Namaste. Bye. Oop.